Hi everybody, welcome to the lecture for 9.3. We're going to be going over the integral test and the P-series test. So to start, let's talk about the integral test. So it's kind of the same song and dance we've been doing for a little bit, where we cloak our series with a function that we call f of x. And they're more or less giving the same information so long as f and the series have some properties in common. So first of all, f has to be positive. So what positive means is that if I'm saying that f is positive, then what I'm really saying is that f of x is strictly greater than 0. And then continuity, so we don't have any jumps, holes, asymptotes, like a piecewise function that's not defined on a given interval would be bad. Okay, decreasing. I think that's pretty obvious. That just means that f of x should be greater than f of y whenever x is bigger than y. So as you move along the x-axis, you need to be lowering your height, your f value. So all this needs to happen only for x greater than or equal to 1. So I'm going to introduce a notation. I'm going to be writing for all. There is a mathematical symbol for this, which we write as an upside down capital A. Okay, the next thing that has to be true for f is that a sub n has to equal f sub n, or f of n. This is the same thing we've been doing. So it just means that the series matches up, that the sequence matches up everywhere on every whole number. Okay, so if you can get all this in line, then what's cool about the integral test is that either both the series and the integral converge, or they both diverge. Okay, so let's see if we can use it in the next example. So this is super important. We always have to check that our function is positive, continuous, and decreasing. Okay, so in this case, we're going to let f of x equal x over x squared plus 1. So we're essentially just copying out the sequence terms from the series. So f is positive for sure, because we're just looking at x greater than or equal to 1. So this is always going to be positive. F is continuous, and f is decreasing. This is true for all. There's my upside down A symbol meaning for all. So for all x greater than or equal to 1, so that's good. And then we also have the additional requirement that a of n, a sub n equals f of n. Okay, so we're ready to go. So now what we're going to do is we're just going to integrate from 1 to infinity f of x dx. So since we have an improper integral, we'll have to use, or we really should use, our limit notation. So I'm going to use a u substitution. This is kind of just a little review on a u sub, but pretty straightforward. So just let u be x squared plus 1, then du would equal 2x dx. So if you did that and then you back substituted, what you would get Actually, I'm not even going to bother back substituting because I'm just going to change the limits of integration. So this is going to be So b is just a dummy variable. I changed the lower limit of integration per the u substitution. If I had done that with b, I would have gotten b squared plus 1. It kind of doesn't matter because b is going to infinity. So if it's b by itself going to infinity, cool, it goes to infinity. If it's b squared plus 1 going to infinity, great, it goes to infinity, whatever. So it doesn't really matter there. And we can see that since the natural log is an increasing function, that this actually, the limit here is infinity. So what we conclude, since we've met all the criteria for the integral test, is that we conclude that since the integral diverges, the series diverges. So that's how that worked. They either both converge or they both diverge. In the first example that we did, we saw that they both diverge. So here's another example. It looks pretty similar. We're going to do the same method. And then there's a really important note that I have to make at the end. So we're going to let f of x equal 1 over x squared plus 1. Then we see that f is positive, f is continuous, CTS for continuous, and f is decreasing. And this is true for all x greater than or equal to 1. And we also have that a sub n equals f of n. So we're ready to use the integral test with this f. Applying the integral test, we set it up. It's an indefinite, or it's an improper integral. So we take the limit as b goes to infinity of 1 to b, 1 over x squared plus 1. And so this is a, oopsies, this is a well-known integral, right? So we all see that this is going to be arctan, hopefully. If not, put that on a flashcard. So we're going to get the limit as b goes to infinity, arctan x, evaluate from 1 to b. Okay, so we want to look at the limit as b goes to infinity of arctan of b, and we're going to subtract from that limit the arctangent of 1. The arctangent of 1 is pi fourths. As b goes to infinity, arctangent of b will go to pi halves. So this is going to equal pi halves minus pi fourths, which is pi fourths. So we can conclude, because the integral converged, we can conclude that the series will also converge. And so you may be tempted to think that, okay, well, the series also converges to pi fourths. No, we don't get to make any assertions about the value of the limit for the series. We just get to say that it converges. And if you did some investigation, you would see a comparison here. So in the bottom right corner, I've kind of highlighted the takeaway for this example. If you take the infinite sum, right? So looking at this piece here, if you take the infinite sum and put it through Wolfram Alpha, which is a great site if you don't already know about it, you would see that your decimal approximation is 1.07. However, for our integral, we got pi fourths, and pi fourths is roughly 0.79. Those are obviously not the same values. So the integral test only tells us that this series converges. It doesn't tell us the value to which the series converges. So this is a great example showing that they converge to two different values. So that's very important.